Suppose we have an expression like this. Log base 7, how about 21 is equal to some unknown value, x. Now, if you tried to calculate this using a calculator, you're probably going to run into trouble because you don't have a log base 7 button on your calculator. So change of base formula can be useful in these kinds of situations. So I'm going to show you how to do it. Now, and we're going to do it by using the rules that I showed you before. So if we want to get rid of this log 7, we can take both sides of this expression as exponents to the power of 7. So we could rewrite this as 21 is equal to 7x. And now let's suppose we want it in log base 10. I can take log base 10 of both sides of the expression. So now I've got log base 10 like that. Of course, I've got log 21 on the left-hand side and x log 7 on the right-hand side. If the thing I'm interested in is the x, then all I have to do is divide both sides of this expression by log 7. And so I'm going to have x is equal to log 21 divided by log 7. They're both base 10. You can plug that into your calculator very simply. And so this is so common that there's actually a formula. And the formula is this. If I've got log base b a, that's equivalent to log base whatever you want, x, a, divided by log base whatever base that you want, b. And that's the formal formula, but you notice it's exactly the same as the way that I derived it originally. So if you remember how to do this, you never need to memorize this formula over here. But if you don't know how to do that on the left, well, you should probably learn. But on the right-hand side, you could answer these questions by memorizing this formula on the right-hand side and then getting the right answer. Right? So let me just add here. X is the base that you want. Right? Can be anything. Log base 1, well, that's not 1, 2, 5, any positive coefficient, and including the natural logarithm, which we're going to talk about shortly. Here's an example. Solve it any way you wish. Use the formula or just do it the way that I did it. Go ahead, press pause. When you're ready to watch, press play and we'll see if you got the right answer. So we've got log 7 base 7, 4, and we want to know what that's equal to. So I'll just set it equal to x. Then I'm going to raise both sides, or I should say I'm going to rewrite this as 4 is equal to 7 to the power of x. And I will then take the log that I want to use. So a nice calculating log is log base 10. So I'll take the log base 10 of both sides. Oops. Like so. And now I've got x is going to be equal to log 4 over log 7. And if I punch this into a calculator, I end up with 0.71241. Here I am on ALEKS. I'm going to plug in my number and I'm going to see if I have the right answer. So 0.712. That's the nearest thousandth, 3 decimal places. I'm going to press the check button. And we got the right answer. Maybe use the formula, maybe use the natural logarithm that I'll talk about shortly. But I got the right answer using log base 10. Before we get into the natural exponential function, let's talk about what a power function is, and then we'll talk about what an exponential function is, and then we can really get into the natural exponential function. So a power function is something like y is equal to b plus mx, where b and m are constant numbers. So you could have something like y is equal to 100 plus 10x, right? And that's just a straight line. Another kind of power function might be something like this. Y is equal to ax squared plus bx plus c. And notice that I could also rewrite it as f of x is equal to ax squared plus bx plus c. Here we've got a and c. They're also constant numbers. And notice what's changing. What's changing is the x. Right? And I'm going to write one last power function. And I'm going to write ax squared. So notice that the base, x is the base. The base is the changing independent variable. And the exponent 2 is constant. Right? I could have maybe even written this as f of x is equal to ax b, something like that. A and b are constants. X is the variable that's changing. And that's what a power function is. The base is changing, the exponents are constant. Now, what's an exponential function? We've kind of already seen them, but let's compare it to a power function. So an exponential function is going to be something like f of x is equal to, well, let's just say, we'll put a number, let's say 2 times, let's say 2 again to the power of x, right? Or maybe I'll just change this to a different number. Let's call it 4, right? And notice that with an exponential function, the base is constant, while the exponent is changing. Right? So here we have, and maybe I'll rewrite this again. So we're going to have f of x is equal to a bx. Right? And in this general form, a is a constant multiplicative, right? It's just some constant number that's multiplying b to the power of x. B is a constant base, and x is the independent and changing variable. Now, an easy way to tell an exponential function from a power function is to look very closely at the notation that we're using. Notice that we have f of x. So we've got an x that tells us the independent variable, the variable that's changing is x, right? And so when x changes, the function, the value of the function changes. So we've got an x here, and we also have an x up here in the exponent. So clearly, this is an exponential function. We've only got one x on the right-hand side, and it's an exponent, so it must be an exponential function. One thing exponential functions are great at is capturing a growing series. So for example, if you're looking at a growing population, so you want to know how population grows, and that's the example we're going to look at in a minute. Or maybe you're interested in finance and you want to understand how a stock price is growing over time. Well, both these can be captured or modeled with a exponential function. Now, I won't offer you a proof, but I'm going to tell you that if we want to know Canada's population in the year 2100, then we can take something like this, Canada's population today, which is about 38 million, and we can multiply it by 1 plus the growth rate. Notice down here, the growth rate is a rate, not a percentage. So it's 0.014, that's 1.4%. Common student mistake when they're asked to calculate these questions. Don't put in the percentage, put in the rate. And if I take this 80 years into the future, I'm going to have Canada's forecasted population in 2100, assuming a constant rate of population growth. If I plug in the numbers, we have 38 million, 1.014 to the power of 80, and that's going to be equal to, using my calculator, about 116 million. So, in the current trend, Canada will have a population of 116 million in the year 2100. And that, of course, is this point right here on the green line. We could find Canada's population using this formula here for any year, right? If we want to know the population in 2040, we take 38 million, we can just ignore that, you don't need to worry about that, times 1.014, and if that's 20 years in the future, if 2040 is 20 years in the future, then Canada's population at this current trend, and assuming it's 20 years in the future, Canada's population should be 50.2 million. Now remember from before, the exponential function, Canada's population looks something like that. Notice that the slope is getting higher and higher, and the population is increasing at an increasing rate. Often in business and economics, that's an unsatisfactory function to work with. So in the previous slide, we had Canada's population in the year, well, in some year, was equal to 38, 1.014 t. Well, we could take the log of whichever base you prefer, log 10, or soon we'll talk about the natural exponent. We can take the log of this, and then we get log population is equal to log 38 plus t log 1.014. And if we do that, notice that our series and I should have log here, log. Our series looks rather linear. An advantage of the log transformation is it's easier to discern a trend. So if we look at the graph in front of you, we can see a linear shape which suggests to us that the growth rate is constant, which of course it is, because the growth rate's right here. It's 1.014, and it's 1.014 throughout every year, never changes.